The locations of maximas and their intensities. The relative single-slit intensity is the intensity at some angle theta divided by the intensity at 0 degrees, which is the central maxima peak, and that is I relative as a function of alpha equals sine alpha divided by alpha quantity squared, where alpha is pi a divided by lambda sine theta, which is a phase factor. We do know about diffraction is the locations of the minimas, and we use that via the path difference equation to understand this. In this equation, we have to ask, what does this mean in terms of the intensity? Clearly, minimas imply that the relevant intensity must be 0. But what are the conditions that you have 0 intensity? Since it is the path difference equation that sets the condition for a minimum, this sets conditions on the alpha parameter. For a minima to occur, sine of alpha has to be equal to 0 for the intensity to be 0. Sine of alpha is only 0 if alpha's integral numbers of pi, in other words, pi, 2 pi, 3 pi, 4 pi, etc. In other words, the alpha locations of all the minimas is in this sequence of pi's. Substituting this condition into I relative, see that the relevant intensity has to be sine of nd pi divided by nd pi squared, and this will always be 0. Plotting I relative, the phase alpha clearly defines when I relative is 0. So if alpha is a factor of pi, 2 pi, 3 pi, 4 pi, which is nd equals to 1, 2, 3, 4, then we see that we have the minimas at these locations relative to alpha. Now that we have the intensity of minimas nailed down relative to alpha, let's focus on the maximas. Unfortunately, these are not so easy. Two-slit interference, we learned that the bright fringes were exactly in the middle between two dark fringes. Picture-wise, I plot I relative as a function of beta, and if I look at MD, I have 0, 1, 2 for the minimas, and then the beta factor would be 0, pi, 2 pi, etc. But this bright fringe here is smack in the middle of these two dark fringes. Diffraction, the maximas are approximately in the middle between two minimas. To see this, we need to handle the intensity function mathematically to see why they are not in the middle between two minimas. To determine the maximum of any mathematical function, we take the derivative and set it to 0 and solve for the critical points. And then we take the critical points and we plug it back into the function. In our case, we take the derivative of the relative intensity with respect to alpha, set that equal to 0, and then go solve for alpha. Mathematically, we write that the derivative of the I relative with respect to alpha, then I take the derivative of sine of alpha over alpha quantity squared, and we get, mathematically, we got to take the derivative of sine alpha over alpha quantity squared. And when you do that, you get 2 alpha sine of alpha cosine of alpha minus sine squared alpha over alpha cubed, and that's equal to 0. And look at the denominator, alpha cubed. This will never be 0. So the only way this quantity could be 0 is if the numerator is 0. So if I focus on the numerator, notice that up here I forgot to add a 2. So that's how I get alpha equal to tan theta. There was an error right there. This equation is a transcendental equation, which means that we're not going to get a closed form algebraic solution. Solutions to this equation can be determined graphically by simultaneously plotting tan of alpha, which I'll do in orange, and alpha in green on the same graph. The points of intersection of these two curves determine the critical points and therefore the locations of the maximas. Plotting tan of alpha and alpha, you could see here that in orange I got tan of alpha, and in green I got alpha here. Now to give you a sense of the tangent here, note that because I have cosine of alpha in the denominator, when that's 0, that means I'm going to get this asymptote, and those occur at alpha equal to half pi, 3/2 pi, 5/2 pi, etc. That's why the tan is looking the way it does. Since the intersections are the critical points, let's look at these. The first critical point occurs right here. at 0, alpha equal to 0, that's the location of the central max. This should be no surprise from calculus, because if I look at the limit as alpha goes to 0, sine of alpha over alpha approaches 1. There's the central maximum. Now 2, alpha not equal to 0 and the secondary maximas. Where are the next intersections of these two curves? Second intersection or crossing is right here. So that implies that that's the second. And then this guy right here is the third crossing. The second intersection is the second critical point that is the first secondary maxima. This is what we would label NC equal to 1, and note that this is close to 3/2, but it's not there. As we'll see here, that value is not 3/2, but is critical value numerically is 2.860 divided by 2 pi, but it's close to 3 pi over 2, but they're not the same. So if I look at the third intersection here, that's the third critical point, and that leads to the second secondary maxima. What you're seeing here is that it's closer to 5/2 over 2 than the second critical point is to 3/2 times pi. If I was to compare that critical point 2 to the third critical point, you see that the second one is some distance away from 3/2 pi, whereas the third is closer to 5/2 pi. That means here that this third intersection is then NC equal to 2. If I look at the actual value of that critical value, I get 4.918 divided by 2 times pi, and that's going to be closer to 5/2 pi. I summarize the first three critical points for this curve. For NC 1, 2, and 3, you can see the actual value, the approximate value, and then the difference between these two. So for the first one, I get 2.860 versus 3. So that's a 4.9% difference. And then I get 4.198 versus 5. That's a 1.67% difference. And then I have 6.997 compared to 7. That's a 0.86. When I get to the fourth, it's really tiny. So if we estimate the first three secondary maximas with this approximate value, we have this percent uncertainty. So that means then, if we know that we're using these values, we know that they're going to be slightly off. First two maximas, they are approximately lying in the middle, with the first maxima having the largest error at 5%. With NC3 or higher, it's safe to say yes, since the actual and approximate values are so close in numerical value. And the intensity with the actual values looks something like this here. So the minimas occur at pi, 2 pi, 3 pi. So the max, first max here, you could see is not exactly in the middle. It's not at 1.5 pi. And then the second one is 2.46. The third one is 3.47. They're close to the middle, but not exactly. And do the maximas lie exactly in between adjacent minimas? The first three maximas, they approximately lie in the middle between adjacent minimas. If you say they do, then there is an error that's largest for NC equal to 1 at 5%, but this error decreases as NC gets larger. If we do accept it, then we can write out a path difference equation for maximas, knowing that A sine theta is approximately NC plus 1/2 lambda, because that puts the maximas exactly in the middle between two adjacent minimas. So the location of the maximas then is given by this path difference equation, where NC of course is equal to 1, 2, 3, etc. One parameter is the alpha, the phase, because that's how we identify the location of where it is in a diffraction pattern, which I will calculate right now for the first three maximas. For NC 1, 2, and 3, the path difference should be then approximately 3/2 lambda, 5/2, and 7/2 lambda. So when I go and I calculate the alphas, I'm going to take a sine and I'm going to plug it right into this equation, which then tells me that the approximate value of alpha 1 is about 1.5 pi, 2.5, 3.5 pi, but for the first three, the actual values, you could see that there's a difference between these two. So if we agree to this condition here, we know that these guys are approximate values. Now that we have the approximate values for the maximal locations, we can write out the intensity values for the maximas. Intensities are most useful when plotted with respect to alpha. Since we've already gone through these alphas, let's just summarize these. So alpha for minimas is nd pi, so it's at pi, 2 pi, 3 pi, etc. Alpha for maximas are approximate, and it's going to be nc plus 1/2 pi. So for the first three, they're approximate, and I'm going to say that after 3, 4, 5, 6, whatever, they're going to be exact. Substitute alpha max into the relative intensity equation. I relative for maximas is then going to be sine of alpha over alpha squared. So approximately, using this relationship up here, I'm going to get sine of nc plus 1/2 pi divided by nc plus 1/2 pi. But note, this approximate value has everything in multiples of pi halves, which means then this will always be 1. I can simplify this relationship. So the numerator is 1, and then I still have the same denominator. That is approximately the relative intensity for maximas. Compute this for the first three maximas. For the first relative intensity of nc equal to 1, I plug in 1, and then I get a value of 0.045. If I now go calculate NC2 and NC3, you see that it's 0.0162 and 0.0083. Turn the approximate to the actual values. These are the three values that we computed. So note that this guy only has 2 sig figs. This guy has 3, that guy has 3. So if I look at the actual values, you could see that this approximation undershoots it in each of these cases. This guy, if I had another sig fig, you could tell the difference, but the percent difference is 4.66, 1.82, and this guy's 0. As I've said numerous times, it's the first two maxes that had the largest error with this approximation. This one you're not seeing because of only 2 sig figs. From my previous intensity plot, I now have the approximate peak values when I'm assuming that approximate model for the path difference for constructive interference. Here's an interesting fact. The intensity function for maximas written with the approximate path difference equation is independent of aperture size. Look, here it is. You see that it has no value of A. Seen before, as the aperture gets larger, the peak intensity increases, and therefore the intensity of the secondary maximas will also increase. But the same ratios of the relative intensity will not change. For example, regardless of the initial intensity, I relative for nc equal to 1 will always be 0.047. And this is regardless of the aperture size.